Hello and welcome back. What is a distribution? So let's have a look. According to Wikipedia, a distribution or a probability distribution is a mathematical function that, stated in simple terms, can be thought of as providing the probability of occurrence of different possible outcomes in an experiment. So very interesting definition. Let's think of what a distribution. So the main takeaway from here is that it's a mathematical function. Let's see what a distribution is for us in terms of data analytics, business analytics, data science. What is a distribution? And we're back to our data set. Probably you were expecting, unless you're quite adept with distributions, you're probably expecting a chart, like a graph, a bell curve or something like that. But that is a common misconception. I specifically didn't want to start by showing a chart because too many people think that a distribution is a chart. A distribution is associated with a chart. Like, a distribution, you always think of a chart. Chart, you see a bell curve, you think of distribution. It's not the same thing. A distribution is actually something that's associated as a function, as we saw. So if we go back here, is a mathematical function that, stated in simple terms, can be thought of as providing probability of occurrence of different possible outcomes in an experiment. It says nothing about a chart. It says nothing about a curve. A distribution is a function which is linked to the underlying data, to the underlying observations. Did it have that word? Outcomes. Well, in this case, outcomes. Well, that's about experiments. In our case, an experiment, in the case of data analytics, an experiment is us picking a random variable from our data. So for instance, here you've got age. So there's our age. There it is. We pick a random one. That's our experiment. What's the possible outcome? Well, the outcome can be only one of the values that we have here. So a distribution is a function which will tell us what is the probability of getting 59 or probability of getting 31 or 40 or so on. Or another way to think about it, probably a better way to think about it is, okay, so this is because that will work better for balance. Variables like that, or in this case, age. Remember we talked about continuous versus discrete? So if this second way of thinking about it is better for continuous variables, which actually age is a continuous variable. It's just rounded here. So because for balance, for instance, you can't just say, okay, so what is the probability if I pick just a random row from this data set? What's the probability of getting, let's say, 197.33? Well, what happens if you don't have that value? Is that probability 0? Well, that's because the best way to think about it, the second way, which I've been mentioning, way to think about it is to say, okay, what is the probability? So this is our data set, and now we're going to add a new random person in here. So, and we know that that person will look like, kind of like the people that we already have. What is the probability that that person will have $197.33 in their bank account? Or what is the probability that that person will be 37 years old? Or what is that probability that that person will be a male or female or be residing in this country or in this country? So that's the better, probably the better way to imagine it. And as you can see, again, it has nothing so far to do with charts or graphs or bell curves and so on. All of that comes later. Well, just now, in a few seconds. But that is an auxiliary element. That is a supplementary thing that will help us aid us in understanding distributions. So let's proceed to that part. We're going to shorten this data set just so we have some space. And we're going to look at two specific variables. So we'll look at age group and we'll look at balance. And we're going to talk about distributions, and you'll see that they're a bit different for discrete and continuous variable. And that's why we specifically picked a discrete variable. So age is debatable whether you want it to be discrete or continuous. In this case, it's probably continuous. Whereas age group, you can see that it's intentionally been made discrete, that there's only certain columns. So this is definitely a discrete variable. Balance is continuous because it's not in certain buckets. All right, so discrete, let's plot the distribution. And the distribution of this variable would look like something, for instance, like that. And, well, the chart for this distribution would look something like that. It's a bar chart, and that's how distributions are presented for discrete variables. Because you only have you have a finite number of categories or a finite number of possible outcomes. If we're talking about experiment, you have finite number of possible outcomes when you're dealing with this variable. So you have, for instance, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70 years old among the customers of this bank. And what is this whole chart about? Well, let's put a 0.3 here. We'll explain just now. That's 10 to 20, 20 to 30, and so on. And so what this chart is showing us is what is the probability of, if we pick a person from this data set, or as we said in the way of thinking about it, number 2, if we just randomly create a new person that enters the bank, what is the probability of them being in this bucket, this bucket, this bucket, and so on. So here it's probably probabilities like 30% of them being here, maybe 25 of them being here, maybe 5% or less than that being here, and so on. So this is what the chart gives us. It gives us the probabilities of the person being in one of these groups. And for instance, here, probability of the person of X, that variable being 30 to 40, equals 0.3, 30%. So that's how the visualization of discrete distributions works. Now let's talk about continuous. So there's continuous. Let's draw that. This is going to be a bit more interesting, a bit more complex, simply because it's continuous. So there's our 0. And the continuous distribution is a continuous line. And what does this line mean, and how does it work? Well, let's have a look. Let's say that's 0.5. It doesn't matter that this is 0.3. These are different charts. Let's say that's 0.5. And let's say that we have balances. So we're visualizing the chart or graph of a distribution for the balance variable. And let's say we have $10,000 here on this chart. So what does it mean that the peak here is at $10,000, or whatever value we get here? What does it mean? So if I draw a line here, can I say that the probability of a person in this data set, or if a new person comes to this bank, can I say that the probability of them having $10,000 in the bank account is 50%? So can I say that? Well, let's imagine that is true for a second. Let's say, yes, that's the case, just like we had with the discrete distribution, that this probability tells you what's the likelihood that this variable will be exactly in this bucket. Well, in that case, remember we said that there's unlimited number of observations here? Like here we only had 5 or 6. Here there's an unlimited number. So how about we take 11,000? So according to this chart, the probability is what? And then we take 12,000. According to this chart, the probability is what? 49%? And then the probability for 12,000 is 42%? Well, they already add up to more than 1. Just these 3 values. And so that can't be the case. So our assumption that what we're seeing here is the probability of that exact value is incorrect. And that's why we can't do that. The correct way of thinking about this is through areas. So this curve over here that we see is actually called the probability density function, or the PDF. And the probability of having this one value is pretty much 0. That's how this function works, and that's how pretty much everything in the world works when you're dealing with continuous variables, because there's unlimited values on this axis. And I'm going to include a separate tutorial about that called the Cantor's diagonal argument. So it's a really cool proof of why there's unlimited values on this between like 0 and $1 billion, or even between 0 and 100,000, why there's unlimited number of observations. And the way you pick a random variable is, imagine that you're throwing a dart at this line. And given that you hit the line, you're throwing a dart at this line. And because there's infinity numbers between 0 and here, there's an infinity number. The probability of you the dart landing exactly in 10,000 is 0. It converges to 0. So the probability of exactly 10,000 is 0, but the correct way of thinking about it is areas. So you take 10,000 plus a little bit, 10,000 minus a little bit, and then the probability of that dart landing inside there is going to be given by the area of this little shaded part of the chart that we've created here. So as you can see, as the area is wider, the probability will be higher. So probability of your dart or your random variable that you pick out of your distribution, because it doesn't have to be from your data set. Your distribution has a function, or this column has a function, a probability density function attached to it, which characterizes the distribution. And so basically you're picking from this probability density function. That's what we said, that second approach of thinking about it, that somebody new enters your bank, the probability that their balance is going to be between $9,500 and $10,500 is the shaded area under the curve over here. And in terms of mathematics, we're not going to go into calculus here, but that is integration. So you need to integrate the area under the curve between 9,500 to 10,500, and that's going to be, or you integrate the curve, and that's going to be your value. That's the probability. So basically, or in simple terms, the best way to think about it is just the area under the curve. And if you extend this area, of course, like if you take from not 9,500, but you take from 8,000 to 12,000, the area is going to be bigger and the probability is going to be bigger. And ultimately, if you take from 0 to a million, probability is going to be 100%. So that's how the probability density function works, and that's the difference between discrete distributions and continuous distributions. Important to understand that distribution, kind of the key takeaway for today is that distribution is attached to the variable or to this, in our case, column itself, rather than just a chart or anything else. And so in this case, you have a discrete distribution. In this case, you have a continuous distribution characterized by a probability density function, both of which can help you understand what is the likelihood of a certain event occurring. Though just the approaches are different. If you have a discrete distribution, it's very simple. You just pick the bucket that you're interested in and look at the probability. In terms of a continuous distribution, it's a bit more complex. You need to find the value you're looking for. You can't just find a probability of one value, because in the world of continuous variables, the probability of one value is always going to be 0. You can only find probabilities of ranges. So the probability of a range is going to be the shaded area under the curve. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.